I took Calc 1, they actually only had me memorize these three. Not that the other three aren't terrible. They're very similar. But that's kind of why I have these highlighted, is because you'll see more of these in general. And then the one under it is just the negative version of it. So if you can kind of have some type of memorization tool, like I just kind of remember, oh, sine and cosine go together, so their derivative will be somewhat similar. Cosine is negative. Same thing with tangent and cotangent, negative. Secant and cosecant, negative. So I'll erase that because it kind of makes the graph look ugly. But, and like, sine, cotangent, cosecants, then it's going to be negative. So that's another tool. But if you have trouble remembering which is negative of what, just try to remember them in groups, I guess, is my suggestion. That's how I would memorize them. Any questions about these new derivatives? Or any questions about the material in general, or log rules? I'm sorry, what'd you say?
Where did these new derivative rules come from? Like, do they just change as we learn more, or what?
So these are the last derivative rules we will learn. It came from the textbook sections 3.8 and 3.9. We covered the derivative of logarithms, which we hadn't covered yet, and then we haven't covered arcsine, arcsecant, arctangent, those kinds of derivatives. So these will be the last derivatives we learn in this class. But yeah, we weren't done when we learned them in.
Well, I was just looking at.
Yeah, you're good. But thankfully, these will be the last ones you have to memorize, I promise. There will be no more new derivatives after this. You'll be able to do derivatives of literally everything if you know all of these basic functions. Which is really cool if you think about it. Well, you'll be able to take derivatives of one variable, or even two with implicit, but... Alright, so... Not sure why this is highlighted. Alright, so let's get started with on the practice exam, which I hope you guys have tried it a little bit. I guess before I start, I do want to... I mentioned it briefly, some very common log rules. Log of A times B, log of A plus log of B. I did cover these during my algebra review, but and then there's natural log of A over B. It's equal to natural log of A minus natural log of B. And then there's also natural log of A to the B power is equal to B times the natural log of A. And ones that you'll see used. And I mean, you should also know the natural log of E is equal to 1. So they're reciprocals, but we will be using those today. But for 6.1, sorry, let me pull it up. They want us to find the derivative, and it's going to be a logarithmic function. There's natural log absolute value of 2 tangent arctangent of x plus arcsine of natural log of x. So I don't want you guys to get confused, but how I will be writing these slightly differently, and you might have noticed that in the new graph. Whenever I see it notated like that, I hate it. I know Dr. Noring also covered that he really hated it too. But I just kind of refuse to write it like that, so I write it as 2, and then I actually write out arctangent of x. that is the same thing as this. It's just you're able to write it out. Plus arc sine of natural log of x. And you an arc sine or an arctangent in it. In his class, I always write it like this on the exam and still be fine. If you prefer this, then you can use it this, but if not, you can just keep writing it like that.
Oh my gosh.
We still got to multiply by the derivative, so d dx of arctangent x. Then we got to take the derivative of our arc sine, which I hope that you guys have started to memorize these because they will keep coming up again and again. They are some of the more difficult derivatives to memorize. But the derivative of arc sine is going to be root 1 over, and it's going to be whatever is inside here, 1 minus the natural log of x squared. And you want to make sure that you wrap that whole thing in the parentheses because it's really important to know if this square is on the outside or inside of the natural log. And then we have to multiply by the derivative of our natural log of x. Any questions so far? We're just using some of our new derivative rules and using chain rule like we just learned last week. All right. So now we got to take the derivative of our arctangent, which is one of the easier ones to remember in my opinion. It's going to be 1 over 1 plus x squared. I also forgot this too, right there, for the arctangent. So that's my bad. Yeah, sorry, I just forgot this 2 right there. Plus, and then we have to take the derivative of the natural log of x, which is just 1 over x. Okay, so we're going to have 1 over x times this 1 over root 1 minus natural log of x squared. Okay, and then from here, we just got to simplify a little bit. So, and then we're basically done with this problem. Is the 1 divided by 1 plus x squared under the 2 from the 2 arctangent x? Yeah. The derivative of arctangent is 1 over 1 plus x squared. But since we have that 2 being multiplied, highlighted in blue, that 2 is going to be on the top. Yeah, no problem. So I'm just going to combine those two fractions, or those two sets of fractions. So we get 2 over 2 arctangent x times 1 plus x squared plus 1 over x root 1 minus natural log of x squared. And then these 2's cancel out, and then we're done. That's it. That's all we got to do. F prime of x is going to equal to 1 over 1 plus x squared, arctangent of x, plus 1 over x root 1 minus natural log of x squared. both those fractions are kind of ugly, so there's no... How we got the fraction? Which fraction? There's lots of fractions. Which line? First one. So right here? Or just, okay. So the derivative of a natural log, so d dx of the natural log of u is equal to 1 over u times du dx. So in this case, like that's our rule for derivatives of natural logs. In this case, ru is equal to 2 arctangent x. So that's how I got this 2 arctangent x down there. And then we have to multiply by the derivative of 2 arctangent x. Does that make sense? Okay, sweet. Any other questions on this problem? This problem just looks extremely complicated because I know our brains tend to look at arctangents. The more letters there is in math problems, sometimes our brains get a little more confused, but once you can get past that, this one isn't terrible. Assuming you know your derivatives, your new derivatives. It might be difficult if you don't know those. So for our next problem, we have g of x is going to be equal to the natural log of e to the x divided by x plus 1. Alright, so there's a couple things we can do here. We could use our natural log properties first. If you want to do that, you can. You should still get the same answer. But honestly, I'm just going to go right ahead and, because if we're finding, here, let me just show you. So if we're finding the derivative, right, of d dx, natural log e to the x for x plus 1, right, our derivative will then be 1 over this whole inside function, right? 1 over e to the x divided by x plus 1 times d dx of e to the x. And then I'm going to write that x plus 1 as x plus 1 to the negative 1 power. So I'm going to do a product rule. Any questions so far? Right, and then we know 1 divided by a fraction is just going to be the reciprocal, right? So it's going to be x plus 1 divided by e to the x. And then we apply our product rule in the second part. So we get e to the x times d dx of x plus 1 to the negative 1 plus x plus 1 to the negative 1 times d dx of e to the x. Does natural log of e dx divided by x plus 1 equal to 1 divided by e to the x divided by x plus 1? Are you talking about the derivative for that? Yeah, it would equal to what you just wrote times the derivative of e to the x divided by x plus 1. So that's what you just said is this first part right here, but we also have to do this part for the full derivative to be correct. But you got that first step correct. That would be the first thing you do. Like I said, if you wanted to, you could rewrite this as the natural log of e to the x minus natural log of x plus 1 and then solve it that way. You should get the same answer. I think the simplification might be a little bit different, but you should get the same answer. Can you send the attendance link? Yeah, I didn't even notice. Like 7 more people have joined. But thank y'all for joining. That's awesome. Thanks for reminding me. All right. So from the second step to this third step, all I did was apply my product rule and then write this as x plus 1 divided by e to the x to make it look a little nicer. Now we just got to take some derivatives. So our derivative of x plus 1 to the negative 1 is going to be, we're going to bring down that negative 1 times, sorry, I just got an email and that distracted me, times x plus 1. Then we subtract 1 from that exponent power. 1 minus 1 is negative 2, plus x plus 1 is the negative 1. And the derivative of e to the x is just e to the x. And I did forget something. I should write it out. So let me move this a little. There should be a times d dx of x plus 1 right there. That won't particularly matter just because the derivative of x plus 1 is just going to be 1. So I'm going to make this a little bit nicer looking before I distribute. So we're going to have this e to the x, and there's that negative 1 there as well, divided by x plus 1 squared. I just brought that x plus 1 to the negative 2 down to the denominator. The derivative of x plus 1 is just going to be 1 plus, and then I'm going to write e to the x divided by x plus 1. All right. So from here, we see that we have common factors. We see that this e to the x is going to cancel out with that e to the x and this e to the x. And then we see that this x plus 1 is going to cancel out with one of those x plus 1s, and then it's going to cancel out with this x plus 1. So distributing that, I can write it out. So maybe it makes a little more sense. We have negative e to the x times x plus 1 over e to the x, x plus 1 squared. I can just write that as x plus 1 times x plus 1 plus e to the x, x plus 1 divided by e to the x, x plus 1. So all I did was distribute that first part to each fraction. And then from here, those e to the x's cancel out. That x plus 1 cancels out with that x plus 1. E to the x's cancel out. X plus 1's cancel out. And now we get g prime of x is equal to negative 1 over x plus 1 plus 1.
Oh.
Now we can still simplify from here, right? These are pretty simple for us to add together. We can just write that x plus 1 as x plus 1 divided by x plus 1. And then adding those two fractions together, we get x plus 1 minus 1
equals
over x plus 1. So we see that g prime of x is going to be equal to x over x plus 1.
So then I have x plus 1 minus 1.
That's our final answer.
Minus 1, this would cancel out and just be x over.
Any questions about this problem? We had to do a little bit more algebra in this problem, but it actually worked out really nicely. We could cancel out some stuff. How did we get the x plus 1 divided by e to the x initially? So the derivative of a natural log, d dx of the natural log of u is equal to 1 over u times du dx. So our u in this scenario was e to the x divided by x plus 1. So that's how we got this part right here. And then since we had 1 divided by that second fraction, that e to the x plus 1, we use keep change flip, right? Keep change flip, so we have 1 times x plus 1 divided by e to the x, and so that's how I got this down there. Does that make sense? Can the derivative of a log also be the derivative of u over u? Are you thinking of the derivative of the absolute value of u? I think that's what you're thinking of. The derivative of the absolute value of u is u divided by absolute value of u. I think that's what you're thinking of. Right here. No, but the derivative of natural log will always be 1 over u, whatever u is. And then you said, why did we get the x plus 1 divided by x plus 1 on the second to last line? So all I did there was this 1 I wrote as x plus 1 divided by x plus 1, because I want to add these bases, I want to add the tops together, so we need the same denominator. We have to find a common denominator. And so that's why I just changed that 1 to x plus 1 divided by x plus 1, because this whole thing is just equal to 1.
Okay.
Yeah, no problem. Any other questions? Alright. Why does the e to the x turn negative? So the e to the x becomes negative when we do product rule up here. So when we take the derivative of this x plus 1 raised to the negative 1 power, we bring down that negative 1 power and then subtract 1. And so that's how that e to the x becomes negative. All great questions. Awesome. Any other questions before we move on to 6.3?
I have a question. How did you get the plus 1 in the second g prime of x, like going up from the answer?
Yeah, so you understand everything in this line?
Yes.
Okay. Well, I'll go from this line. So from here, I just distributed that x plus 1 and e to the x to each of the fractions. So that's the only difference is this x plus 1 is being multiplied right here and here. And this e to the x is being multiplied there and there. And then from there, I just found common things on the top and the bottom, right, to simplify. Everything's being multiplied or divided, so we're allowed to cross-cancel. So this e to the x and that e to the x will cancel out. This x plus 1 and that x plus 1 will cancel out. We're still left with 1 x plus 1 there. And then this e to the x cancels out. And then this x plus 1 cancels out. And if everything on the top is equal to everything on the bottom of a fraction, that fraction is just equal to 1, which is how I got that 1 right there.
Oh, okay.
And then we're just left with that 1 x plus 1 and then this negative sign in the first fraction.
Oh, okay. Thank you.
Yeah, no problem. He would definitely give you most of the credits. I want to say that he probably would accept it. I think on this one he did say to simplify fully. No, that's on 6.3. I think he would probably give you full credit. I mean, you've gone most of the way. If you miss that on an exam, I wouldn't worry too much about it because you'd only get a little bit of points taken off. Like, if you did everything else right and you just didn't simplify it that one step, like, you already simplified it a decent amount, so. I think it depends on how simplified. Like, there's been times where he hasn't taken points away from me for not simplifying, like if I forget like one step, but if you don't simplify at all, like, I can see him taking off more points. I think it just depends on how much simplification there is. But most of the time you can expect a -1. Right, and then 6.3 is going to be h of x is equal to the natural log of x minus roots x squared minus 1. So again, we're doing derivatives of logs. So h prime of x is going to be equal to, we know a derivative of a logarithm is just 1 over whatever is inside. So we know that's just going to be 1 over x minus root x squared minus 1. Is it minus or plus? It's minus. Okay. Is it a plus? Because I changed it halfway through on my answer sheet. I need to fix that. Could someone look on the practice exam? It's a minus. Okay, sweet. And then times the derivative. Yeah, I'll just need to fix that on my answer sheet before I send it. That's okay. It's not too hard. And then we need to multiply by the derivative of x minus roots x squared minus 1. I'm going to write this root as a 1/2 power, because that'll make it a little easier for us to take derivatives. Alright, h prime of x, the derivative of x is just 1, and then taking the derivative of x squared minus 1 to the 1/2 power, we're going to have to use our chain rule. Right, so we bring that 1/2 power down, subtract 1, so it's going to be negative 1/2, times the derivative of x squared minus 1. Alright, so this first part staying the same, and then taking the derivative, I'm just going to bring this part, the 1/2 x squared minus 1 to the negative 1/2 down to the denominator of the problem. Roots x squared minus 1. Taking the derivative of x squared minus 1 is just going to be 2x. Derivative of x squared minus 1 is just this 2x right there. Any questions up until here? Because from here it's just some algebra. Also, those 2's are going to cancel out. Can I repeat the top again? Yeah, so when we take the derivative of this x, x minus x squared minus 1 to the 1/2, we take the derivative of x, so that's just going to be 1. Then we're taking the derivative of this x squared minus 1 to the 1/2. We bring down that 1/2 power, subtract 1, so we get x squared minus 1 to the negative 1/2. And then we have to multiply that by the derivative of x squared minus 1. Derivative of x squared minus 1 is 2x, and that's how we get that in the numerator of this fraction. Yeah, no problem. Alright, so now I'm going to do something very similar to what I did in this last problem. So chain rule is you're kind of applying it all the time without even realizing it. Like if you're taking the derivative of like an x squared, right? You use power rule for that, d dx would be 2x. But then secretly you're taking the derivative of x, which will always just be 1, because that's your inside function technically. So even with power rule, you're using chain rule. So it's kind of like you want to keep taking derivatives until your derivative is just 1 at the end. So whenever we learn power rule, we're already kind of using chain rule, but we just didn't know it yet. Yeah, so it's kind of like if you're thinking, what's my inside function, and then the derivative of that is 1, then you're good. There's no more chain rule. Yeah, no problem. I hope that helped. There's probably a better way I could have explained that, but that's kind of how I think about it. And then I'm going to do something very similar to what I did in our last problem with this 1. I'm going to write it as x squared minus 1 over x squared minus 1, or the root of it, that is. So this first part staying the same, x minus x squared minus 1. And then I'm going to write that 1 as x roots x squared minus 1 over roots x squared minus 1 minus x over roots x squared minus 1. And now we're able to add these numerators together. So we get h prime of x to x squared minus 1. So we get root x squared minus 1 minus x all over root x squared minus 1. Alright, and now we're going to multiply these two fractions together, right? So we're done with derivatives. At this point, we're just doing algebra. So we're going to multiply these two derivatives together, not derivatives, these two fractions together, to get root x squared minus 1 minus x over root x squared minus 1 times x minus square root x squared minus 1. So I don't know if you guys can see this, or I'm sure you do see it. These two are very similar, right? We want to factor it out so it looks a lot nicer, but we see it's swapped. On our numerator, our x is negative, and then in our denominator, our root x squared minus 1 is negative. So all we're going to do to be able to factor this out is we're going to factor out a negative 1, and either the numerator or denominator, doesn't matter, wherever you feel most comfortable with it. I'm going to factor out a negative 1 from the numerator, so we factor out a negative sign. So now our x becomes positive, and then our root x squared minus 1 becomes negative. And then we're still left with our same denominator. And now we see that these two are exactly the same, so we can cancel them out. And now we're done. Our h prime of x is equal to negative 1 over root x squared minus 1. Any questions on this one, or any comments? Taking the derivative of logarithm is going to be very similar every time. We're just bringing whatever's on the inside of that natural log below a fraction, and then multiplying by whatever the derivative is on the inside of that log. I think we've had a log in all of these problems. Yeah, we have. Can you explain the chain part again? So like what I said earlier when I was explaining it to Michelle. Like the, so for chain rule, right, I'm just gonna, I won't write it in that color, I'll write it in a better one. So for something like the natural log of sine of x squared, it's like the derivative of this, right? You want to keep going until whenever the derivative of your inside function is 1, right? Because we've been using chain rule all along, you just didn't realize it. So we would do our outside function, right? Like chain rule, we would go outside, inside. You see our outside function is this natural log, right? So then this would equal 1 over sine x squared. And now we have to multiply by the derivative of our sine x squared, right? So that's one chain. And now, taking the derivative of sine, our derivative of sine is cosine. So we have cosine x squared divided by sine x squared times, and then we have this another inside function, x squared, times the derivative of x squared. So that cosine divided by sine would actually be cotangent x squared as one of our reciprocal properties or quotient properties. And then derivative of x squared, you can think of this x as in parentheses, is 2x. And now using chain rule again, our inside function would be x squared. We do, or not x squared, just be x, so it'd be d dx of x. But the derivative of x is just 1, right? So you see you're done whenever you get this one part. Does that kind of make sense? Well, you don't have to write that. That's just me illustrating that you're done with chain rule, right? If you don't see it, you should do that to see it. You're done with chain rule, right? You have to think of what could possibly be my inside function, and then pick that out, and then try to take the derivative of that. And if the derivative of that is 1, then you're good.
So I get that part, but I was wondering, when you had the 1 over x minus square root x squared minus 1, and you multiplied it by what you were subtracting, I was wondering where you got that from in the brackets.
1 over x squared minus 1. So, open up the step.
The one before it.
Okay. So which part specifically are you asking about?
So how did you get to multiply it by that?
Oh, by this x squared minus 1?
With that whole entire bracket.
Well, I just did it with, I just multiplied x squared root x squared minus 1 to this one fraction, right? Just to this fraction. This part stayed the same from here to here.
Oh, okay, I see.
And then this part stayed the same. So all I did was, I wrote 1 as root x squared minus 1 divided by root x squared minus 1.
Okay, I think I just wrote it wrong on my paper. That makes sense.
Awesome.
Thank you.
No problem.
Right, she basically found comment about it.
Any other questions? We're about to get into a fun one. Might not be so fun for you, but I really like logarithmic differentiation problems. What's your question? See the illustration I just did? Yeah. This part? sorry if I emphasized that you've always been using chain rule. I just thought whenever I learned that, I was like, that's really cool. You know, we were kind of using chain rule all along. It's just, they didn't formally teach it to you. Why find the derivative of x? You don't need to. You absolutely, you do not have to write this stuff on your test. Like, that's just illustrating that you've been using chain rule all along. X is your inside function in x squared. So x is your u. So what's the derivative of du dx? It's just 1 in this case. Like, you absolutely do not have to write that on your test. That's just me illustrating that, oh, we're done with chain rule here. If you're struggling to see when you're done. Does that make sense? Like, it's just purely illustrating that we're using chain rule even if we don't explicitly state it when we're using like a power rule. No problem.
I have a question. Why does like on the last slide? Why does wait, can you go back?
Oh yeah.
Why does 1 over sine turn into cosine over sine?
Because the derivative of sine is cosine, right? We take the derivative of sine right here, and the derivative of that is cosine.
Okay.
All right. So now we're going to go on to 6.4. That last part when you're on the test. Yeah. I mean, you don't have to remember this part. That's just illustration purposes. So if you're talking about that, you don't have to do that. I mean, oh, for 6.3, yeah. Yeah, he did, for that one, he did say to simplify fully, and the simplification for that one was, for 6.3, was not the best. It was definitely, it took me a second to think about it, because I think just all the square roots can get a little tricky. So, 6.4 looks really nasty, but it's not that bad. If you know, well, it's kind of, if you're comfortable with logarithmic differentiation, then it's not that bad, but I know you guys are just learning it, so it's definitely a little tricky for you guys. Sorry, I'm just trying to look at it on my paper. 3x minus 5 to the 4/3 times x cubed plus 2 to the 4th. Alright, so whenever you see something that's like nasty looking like this, or it's like, oh my god, I'm gonna have to do so many products, so many quotient rules, I don't even want to think about it, you should probably be using logarithmic differentiation. So the first thing we're going to do, I'm just going to write this as steps, I guess. Set p of x equal to y. Alright, so that's what we're going to do. We're going to write p of x is equal to y is equal to the same thing. I don't want to write it again, just for that one step, so I lost a cubed. So that's our first step. Right. Our step 2 is we're going to take the natural log of both sides. Right. So now we're going to have p of x is equal to the natural log of y is equal to the natural log of this whole thing, this x plus 7 to the 2/7 times x squared minus 2 to the 3 over 3x minus 5 to the 4/3 times x cubed plus 2 to the 4th. And this actually makes it really easy for us because we can now use our log rules, our log of a times b and log of a over b, and the log a to the b. It's so useful here. I can't stress it enough. It's really cool how it turns out actually. So separating all these logs, there's going to be 4 of them, right? We see the difference. So there's 4 different things here. So there's going to be 4 different logs. So we're going to get the natural log of, and we bring all these exponents down in front of the natural log. They become constants being multiplied by that log. So it's going to be 2/7 natural log of x plus 7 plus 3 natural log of x squared minus 2 minus 4/3 natural log of 3x minus 5 minus 4 natural log of x cubed plus 2. Alright. And now we're going to take our derivatives. Yep. So we're going to wrap everything in d dx. And then I'm just going to write quotation marks for right now because it's just the exact same thing. So I'm about to take the derivative of it. Alright. So p prime of x, the derivative of natural log of y is going to be what? Remember, we're taking the derivative of a y value instead of an x, so there's something more we have to add to it. But if we just treat it like an x, what would it be?
That'd be 2,
1. Yeah, exactly, Sophie. It's going to be 1 over y. Just like the natural log of x, the derivative of that is 1 over x. Derivative of natural log of y is going to be 1 over y. Now, do you recall back when we learned implicit differentiation whenever we took a derivative of a y? Yeah, exactly. We have to multiply by dy dx. Doug and Amon, you guys are exactly right. We have to multiply by dy dx whenever we take the derivative of a y. And now I'm going to take, chain rule. It's because of chain rule is why we have to multiply it by dy dx. And then we're going to take the derivatives individually of those 4 different logs. So first we're going to have 2/7 times 1 over x plus 7, right? Because our first one is x plus 7 times the derivative of x plus 7 plus 3 times 1 over x squared minus 2 times d dx of x squared minus 2. Sorry, this is going to get a little long for a second. Minus 4/3 times 1 over 3x minus 5 times d dx of 3x minus 5 minus 4 times 1 over x cubed plus 2 times d dx of x cubed plus 2. I don't even know if I can zoom out all the way, but that's what we're going to get when we do our first derivatives. And then from here we have to do our derivatives of, here let me highlight so it might look a little nicer. Just so you can see where I got these from. And so we can clean this up a little bit. And then we have to take our next 4 derivatives, our x plus 7, our x squared minus 2, 3x minus 5, and our x cubed plus 2. So we still have this p prime of x is equal to 1 over y dy dx. And what's the derivative of x plus 7? Yeah, it's just going to be 1. You guys are right.
and then the 7
And then what about the derivative of x squared minus
All of
2?
which is basically okay.
Yeah, 2x. Exactly right.
Plus
And then
3
what
times
about
x.
3x minus 5?
Wait,
3? Yeah, exactly. 3. And then, last but not least, what about the derivative of x cubed plus 2?
3x.
3x squared. Yep, you're completely right. Over x cubed plus 2. So we're back to one page now. Alright, so now we can simplify a little bit. You see this 3 and that 3 is going to cancel out. Yeah, so let's write this one more time and then we can get into our third
Then
step.
wouldn't we like cross this?
1 over y dy dx is equal to 2 over 7 times x plus 7 plus 6x over x squared minus 2 minus 4 over 3x minus 5, and then minus 12x squared over x cubed plus 2. Alright, so step 1, set p of x to equal to y, and then we took the natural log of both sides and simplify and take the derivative. Forgot to write that part.
No.
And then step 3 is going to be multiply both sides by y and substitute. Right? Just like our implicit differentiation, we want to get that dy dx by itself. And we already know what y is. We set y equal to p of x, right? This is what y is equal to. So we're going to multiply both sides by y. So we get p prime of x is equal to dy dx is equal to y times 2 divided by 7x plus 7 plus 6x over x squared minus 2 minus 4 over 3x minus 5 minus 12x squared over x cubed plus 2. Right? And then all we have to do, and then we're done with the problem, is substitute our y back in. So p prime of x equal to dy dx, and our y was equal to x plus 7 to the 2/7 times x squared minus 2, or x squared minus 2 cubed divided by 3x minus 5 to the 4/3 times x cubed plus 2 to the 4th. And we're going to have the same thing in brackets. 2 over 7 times x plus 7 plus 6x over x squared minus 2 minus 4 over 3x minus 5 minus 12x squared over x cubed plus 2. It's 2/7. Sorry, it's my bad. Yeah. And that's our final answer.
So you're just basically
Any
putting it
questions on
back.
this one? We will be going over one more problem. It'll be very quick. We're going to do 6.10. So the last problem on the exam. But any questions? I try to break it down to where it's not, it's going to be a little formulaic. How did the y show up? So when we took the derivative right here of this natural log of y, we had that 1 over y. We multiplied y to both sides to get rid of that y near the dy dx, and we got that y right there. We just multiplied both sides of the equation by y, and then replaced y because we said up here that y is equal to p of x.
I have a question on why in the beginning, like we subtracted the 4 over the 3x minus 5 and subtracted the 12. Like, why did we start subtracting?
So for rules of natural logs, we're allowed to, natural log of a divided by b is going to be natural log of a minus natural log of b. So that's why these two are negative, is because they're in the denominator, so we have to subtract them.
Oh, okay, that makes sense. Thank you.
No problem. What is the last term in the answer? It's going to be 12x squared over x cubed plus 2.
So just basically bring everything back to its form. And then have this one.
Okay, so I do want to go over. I'll try, if I have time, I will go over this again on Thursday. But I do want to talk about 6.10 a little bit. This problem theoretically should be really easy, because he basically gives you what you're going to use for it. So hopefully you guys have the practice exam pulled up. But the problem is the limit as z goes to infinity, don't freak out if you haven't looked at it yet, is of 1 minus pi over z to the z. So they want us to find this limit. But he gives us this limit on the test that we can use to help solve it, which is the natural log, or not natural log, the limit as z goes to infinity. Is it x cubed plus 2 or minus? Because earlier it was a minus and then the answer is a plus. I think I kept it x cubed plus 2 throughout the whole thing. It started as an x cubed plus 2 up here. You might have just accidentally wrote it as a minus somewhere in your own work. Yeah, it happens. It happens to me all the time. On the test, he gives you the limits as z goes to infinity of 1 plus a over z, or I think he uses x in this other one, so let me change that. This is x is equal to e to the a power. So he gives you this on the test. So all he wants you to do is find the limit of that left thing using the pattern of this right thing. So we see that there's positive, and then there's an a here. So e is being raised to the positive a. Now looking just at that, what do you think that this left limit will be? What's the difference?
To the z?
Is the power z? Yeah, the power is z. It's the variable z.
So
Negative e to the pi. Close. Very close. Yeah, it's going to be e to the negative pi. Yeah. It's just going to be e to the negative pi. And he could have anything up there. He could have a negative, like that's just the one on the test, but it would be e to the negative pi. Like he could have a negative, like natural log of 2, and it would be e to the negative natural log of 2. Or he could have, I mean, I don't really know. I think that he just wants you to, there's not a whole lot of work for you to show for this one, to be honest. It's a negative from the minus sign. Yeah, so if this is negative right here, the exponent will be negative. If it's positive, the exponent will be positive. But another example, this could be positive. This could be positive e, and then you could get e raised to the e power, or you could have a negative sine of 3x, or it's a negative sine of 3 or something. Let's not make it so simple. Let's do negative sine of 1/3, so we wouldn't be able to do that. So it'd be e to the negative sine of 1/3. Does that kind of make sense? You're just kind of following the pattern is all for this problem. So hopefully this should be an easy problem on the test. I did ask him about it on Monday. Today's Tuesday. Monday about it, and he said he was gonna give you this limit on the test. This will be given, and the limit he gives it should be in very similar format, and it's just gonna have you're just gonna have to apply what this looks like. That's it. So it shouldn't be too hard. I am going to send my attendance link one more time, but that's it for today's session. Yeah, thank you. Thank you. Good luck on this exam. Hope to see you guys on Thursday. I'll be here for a couple more minutes if you have any questions. Yeah, no problem. Have a great night. You too. Have a good night. I'm so glad they help. No problem. Thanks for coming. I appreciate it. Yeah, you too, Stephanie.